So last time I described one application of random walk, which is essentially called hitting time or spreading time on a graph. And it was a kind of spatially constructed structure where there was a binary tree and glued back onto itself, and then you can demonstrate that yes, in one case, the classical case, the walk takes forever to reach the other side, but in a quantum case, it does a much better job. And the essential idea in that was that when you have quantum superposition, you essentially reduce the dimensionality of the space over which the distribution takes place. It's a wavefront, and wavefront proceeds at a constant speed in all directions. While in a Brownian motion type random walk, you generate some zigzag trajectory, and only one trajectory can be constructed at a time, and then you have to construct many trajectories, and it takes a lot more effort to do that. So today I'm going to describe one more application. It is much more general than just the hitting time, and this application has come to be known as a spatial search. And the idea behind it is a search process in a database, but the database is distributed over many different locations. And you are still trying to find an object of interest, but you have to wander around to various locations in the database till you find what you are looking for. And that wandering around part is taken care of by the random walk. That is the essential structure. So the setting is distributed database. And the strategy which is used is essentially something which has been called Hamiltonian simulation. This is the same logic by which Grover constructed his algorithm, but his algorithm was not for a distributed database, it was for a single database. And here you follow the same logic and see what can be achieved. So the mathematical part of this Hamiltonian simulation is you generate a unitary evolution operator using some Hamiltonian, and this Hamiltonian consists of various parts, and what is essentially done is that the kinetic energy part of the Hamiltonian, which is mapped onto random walk, and there is a potential energy part of the Hamiltonian, which is mapped onto some kind of attraction towards the desired item that you are searching for. And mathematically, what was implemented in this scenario by Grover is that he used basically projection operator for both these scenarios. One of them was a projection into the average state, And what it does is you write down a matrix, it connects every point to every other point. And this can be understood in various scenarios. So in graph theory language, it is called a complete graph. Complete graph means every vertex is connected to every other vertex, and this matrix is such that it has all amplitudes which are equal. There is a different way of looking at it from the physics perspective. What is the kind of uniform projection which gives this kind of interaction? And in statistical mechanics, the scenario is very similar to what is called a mean field theory. Mean field theory means the effect you get at one point, it's average over all the others. And all the other components are basically added together in an unbiased manner. So it is equivalent to this kind of a structure. And then you can yet another version which is connected to this feature can write down, which is a d going to infinity limit of the graph. Essentially, it is understood in some intuitive fashion how many neighbors you have for a particular point, which it defines the dimensionality of the system. And if you let the dimension goes to infinity, well, everything becomes neighbor of everything else, and that is in this particular scenario. This is more rigorously obtained even in the case of mean field theory, that if you have some model and you want to study it in statistical mechanics, you can obtain the solution as a function of dimension. The simplest model, even the Ising model, will behave very differently in d equal to 1, d equal to 2, d equal to 3, etc. And then you can ask what will happen when d goes to infinity. Well, you will get the mean field theory description, which could have been obtained in some other way by just averaging all the interactions. So mathematically, all these features are connected, and from the distributed database description, this d going to infinity limit is something which can be understood much more easily, and Grover's algorithm essentially correspond to what we'll consider spatial search, and we can take the limit dimension going to infinity, you will recover Grover's algorithm. So that was one part of the potential, and the other part of the potential was the projection operator for the target state, which was just these objects. So target states have attractive potential, and on the non-targets have the zero potential. So it's now becoming a scenario which you can kind of visualize. You have a landscape, and essentially it is flat except for certain location where there is a dip or a hole, whatever you want to call it. you are performing a random walk going all over the place, and when you come near the hole, you will fall inside. So that is the physical picture of what is called the Hamiltonian simulation. Okay. So now one can ask what will happen when you have not this Grover's algorithm, but algorithm which you are going to use as a finite value of d. Incidentally, in this evolution, Hamiltonian is given by this, and the time you can adjust in some manner to get the magnitude of this kinetic energy and potential energy adjusted to your taste, and that is something which remains as a free parameter. What Grover used was a particular situation where this operator was minus Rs times Rt, where R and S and Rt were reflection operators corresponding to these projection matrices, and the magnitudes were such that this transformation are the largest. In some sense, this correspond to, in this notation, to taking the time equal to pi, because these are projection operators, they have eigenvalues 0 and 1, and you exponentiate it, and the eigenvalue then will come plus 1 and minus 1, which are the eigenvalues of the reflection operators. But now we can generalize this to the case of arbitrary dimensions. So you can have various situations, and the common thing which is used in many physical models is the hypercubic lattice. You can have what is called a regular graph, which I defined last time, as every point has a fixed number of neighbors, and the number of neighbors is essentially what controls the dimension. Then there is even more unusual things you can do is look at geometry, which is fractal, where you don't have a unit cell of the crystal as in the case of hypercubic lattice, but you have some recursion relation which tells you how the graph is connected from one point to another, and various possibilities are there in this kind of a structure, and they can all be studied. So I studied several of these things many years ago, and there are several papers which I have written, etc., and some of them developed even into a PhD thesis. But that is a long story. If you want to go into great detail, yes, you can do some mathematical analysis, you can do numerical simulations of the algorithms, etc. And I have done that all with my students. But I will not go into great details about what the detailed results are. I will restrict myself to describing the main ideas and the patterns which came out from all this analysis. So let me first just quantify this various type of graph, and from that give a simple bound on how quickly this spatial search succeeds. So there are two bounds. So there is a and that arises by looking at this generic picture, and the two bounds are essentially the limits of the Grover's algorithm, which is the d going to infinity limit, or the fastest possible spread on a graph, because everything is connected to everything else. If the connectivity is less, you will take more time to again distribute, search the distributed space, and that is why it is a lower bound. And this omega is a symbol for the lower bound in the quantum complexity. So one of the bound is this square root of n. So this is and the second bound comes from the fact that even with a spread of waves at a uniform rate, you will require some time to cover the whole lattice. So if you are in a d dimension, the linear extent of the lattice is the total number of vertices raised to power 1 over d. You can easily visualize it for something like a hypercubic lattice. You can define a one dimension, say, as L, and the total volume is L to the power d. And the total volume is the number of sites which you are working with. So this is a linear spread of waves. And certainly you can't do faster than that, because that is dynamics which you are going to use in any case, and both of them have to be obeyed, and that gives you some idea about what the behavior is going to be like. And I will give the results. The details will have to come from actual numerical simulations and some analytical proofs, but the results are important and they are quite straightforward. So if I take d equal to 1, then this factor doesn't help. This one dominates. And this, so search basically becomes order n. You just have to go in a one-dimensional lattice from one end to another. You don't know where the target is. Just have to search for it. Even if you have a linear spread, it doesn't help. And classically, you would have done the same thing. Just looked at all the points one by one, and that is also order n. So this is no there is no difference for classical versus quantum. If I take dimension which is larger than 2, then this term can be ignored, and this term which is dominant, and that wins. It's a larger power. So here the bound is order square root of n, and this is a quadratic speed up, which turns out to be achievable in practice. Okay. Remember that the classical work for the spatial search will always be order n. You just don't know where it is, and you just have to randomly go and look the places one by one. But the quantum algorithm will differ, and this scaling is coming from Grover's algorithm. And when I say it is achievable, is you can show that the behavior is order root n. What is different between Grover's case and this particular case is there is a proportionality factor in front of square root of n. And when d is not infinite, that proportionality factor is going to be larger in case of this distributed database compared to the value for Grover's algorithm. So here this explicit scaling factor is that what I wrote down is q is equal to pi by 4 root n. This is Grover's case, and it will be some c root n with c greater than pi by 4 for d which is not infinite. You take a limit, then you will get pi by 4. So it is just the overall proportionality constant which you pay the penalty for search in dimension bigger than 2, and that is quite useful to know because, well, many times you can arrange the distributed graph in a certain manner and you don't have to go all the way to maximizing the connectivity. Even with a finite connectivity, you can get quite a good amount of speed up. So this is a generic. Such results are known in classical graph theory also. You literally don't have to go to high connectivity. So yeah, you can have fast spread of signals with finite amount of connectivity, and this is a very practical problem. As a matter of fact, it is used all over the place in designing internet. And that is all classical, but still such advantage can be obtained. And people have studied the kind of graphs which allows you to do that. There are specific design, and if you want to look at it in some more detail, there is something which is called Ramanujan graphs. The same Ramanujan who is famous for all kinds of results in number theory, his name has been attached to this kind of graphs for various reasons, but they are important in designing this kind of networks with high connectivity. No, sorry, finite connectivity, but very fast spread of signals. Of course, it is nonlinear in the sense that you have short distance connection and also you have long distance connection all mixed together, but there is a specific system and there is an algorithm which allows you to design that. And it's important because internet uses this kind of geometry a lot of time. That is a kind of diversion, but the same kind of feature appears in the quantum world as well. Yeah. Well, it's you have to take the largest value because both of these things are lower bound. So omega root n is also lower bound. Omega n over n to the power 1 over d is also the lower bound. And so the total lower bound is the largest of the two lower bounds, whatever it is. That is what I mean by that notation. Okay. So this is a sort of generic feature, and something peculiar happens for d equal to 2, because then these two values coincide. So that is something in the language of statistical mechanics is something called a critical dimension, and what it means is there are two different dynamical properties which compete with each other. And whenever that happens in physics, the label is it's called critical dimension. And the generic behavior in many of the statistical models in case of critical dimension is that you will have logarithmic corrections. Now, how that logarithmic correction arises is a complicated story in terms of critical dimension, but it just means that the scaling, whatever this kind of thing, is not just root n. So you get extra factor of log n to the some power. And one very simple way to understand in this particular scenario is this language which is often used for propagator is integration over momentum in d dimension, and this k square, which is a behavior for the Laplacian, which was a generic operator describing the walk, and this is dimensional and this function develops a singularity at d equal to 2. That singularity is logarithmic. And that is the way you can try to understand why these extra factors appear. People try very hard to make it just root n without any log n. Nobody has succeeded. Okay. And the reason is there is no way to get rid of this kind of singularity. There are various momentum modes. The Laplacian is fixed because that is the structure of the operator which you have, and you just integrate over the momentum. It doesn't matter whether the integral is what you call infinite or whether it is over a Brillouin zone. The singularity will come at k equal to 0. There's a log singularity which you can't avoid. For d greater than 2, the singularity at k equal to 0 is absent. Okay. Because you will have k raised to d minus 1 times dk, and this has to include. That is the most important part. That the singularity is sitting at k equal to 0 mode. K equal to 0 mode in position space correspond to uniform distribution. So it is always allowed, but it can create an additional correction and it can lead to this kind of behavior. And the best algorithm which is known for this d equal to 2 case is p equal to order root n times log n. And to obtain that, yet another trick was used. This was the algorithm constructed by Tulsi. He was a student at IISc at that time, many years back. And the trick which he used, he arrived at it by all kind of mathematical jugglery, but it has a graphical interpretation. And that amounts to looking at a graph that is, I will write it in a two-dimensional, some lattice. Things like that. But he added one extra structure to this square graph, which amounts to putting a loop on the target site. Okay, so this is the target. And what it does in terms of a random walk is, if you are at another point, when you are here, you will go to its neighbors. But when you end the target, there is a certain extra probability that you will just remain there. You will not move. Technically, you are moving along the loop and just landing up back at the starting point. So the probability at being at the target gets enhanced in a certain manner. Or rather, once you reach there, you don't move away that easily. Yeah. So that is why you have to include it as a part of this particular operator, which is a projection operator where you are going to put the potential, and that is put in by hand. I will write down the mathematical structure for that, which I have not done so far. But what this amounts to is, I discussed this wave dynamics in a generic, this Klein-Gordon kind of equation, where you had neighbors and you had a wave packet which you just spread out. Now, what this does is there is a certain amplitude for the wave packet to remain where it is. It doesn't move. And there was an operator for that in the Klein-Gordon equation, which was just the mass. So mass was a local operator. The Laplacian was a movement operator. And mass being an identity operator, it doesn't do anything. If some amplitude is there, it just keeps it where it is. So this is a mixture of mass at target site and Laplacian elsewhere. This corresponds to this nature of the graph. So you have to introduce in the Hamiltonian a position dependent mass. And the position dependence is exactly the one which is given by this target projection operator. So you add an extra mass term on top of whatever this potential you have inserted in the algorithm, and then you find an algorithm which has this kind of an extra loop in the graphical language, and it gives a little bit better convergence in terms of getting the probability enhanced at the place where you want to go. So this is one more twist, etc. So it's a equation, but it breaks translation invariance. The mass is not that everywhere. It is there only at the target site. Okay. So this is a summary of the kind of general results which you can get out of this Hamiltonian simulation picture. And now let me give the mathematical structure. Which basically is very similar to what Grover's algorithm does. So there is a operator which, instead of being the reflection operator in uniform state, which was RS, now we are going to replace it by a generic diffusion operator based on the random walk. And then this is left unchanged. And it had only two values, +1 and -1, and that will still come from the oracle. Okay. And then this Q, whatever I am calling the query, is a number of uses of oracle. That remains unchanged, and then you can find out how this algorithm works, some part analytically if you want more accurate values. For example, finding this coefficient in front of square root of n, you have to do some numerical simulation. So there is still a lot of freedom to choose this diffusion operator. Okay. So because it's some what you call behavior similar to Laplacian, but it's not unique. on the graph you can define some connectivity in many different ways, and all of them will be some approximation to the Laplacian, and they all can be used as some kind of a structure, but some versions are easier to simulate than the others. So the structure which is used more often, which is what I used and which is what many other people have also used, that a ds is something which I earlier called as a flip-flop walk, which was a description of the Klein-Gordon equation, or the D'Alembert solution to a general wave equation. So is a what you call popular choice. And it has both the space degree of freedom and the coin degrees of freedom built inside by construction, and then you alternate these two operators exactly like in Grover's algorithm and figure out how the evolution will take place, and this ds is defined for any regular graph. So that is one structure, and yeah, the way this thing is formulated is you have to introduce yet another label to take care of the mass, which can be done by enlarging the Hilbert space by one more factor of 2 to count that whether you are applying this mass operator at that particular location or not. And that is how the algorithm constructed by Tulsi is formulated, that you sometime are in one space, sometime you go to the other auxiliary space, and if you are in the auxiliary space, essentially you don't move, you remain there, and then you can come back after some time depending on the value of the mass you stick in. Anyway, so that requires some technical construction if you want to write an operator for that. I'm not going to do that right now. But there is yet another feature which is present even for this flip-flop walk, which is interesting, and that has to do with what I called as a graph, which is a fractal. So how do you define a fractal? And the definition is a recursive instead of a iterative definition. Recursive means that at this point you have so many neighbors. Go to the next level point, again you have so many neighbors, and you keep on going. For example, a binary structure like this, you keep on going, defines a kind of fractal. Of course, it has a trivial dimension because it's well, 2 branches at every point, and you can work out how the volume scales with the number of steps that you take, etc., etc. But you can do it much more generically in this particular recursive method, and the new feature which arises is that it has two different definitions of dimensions, and one of them is called Hausdorff dimension, which basically describes as the scale of the fractal grows, how fast the number of points inside that grow. Okay, so it's a physical space volume which define the Hausdorff dimension. And there is something called a spectral dimension, which says that on that fractal you define a Laplacian operator. The fractals can still be regular graphs, so you can define a Laplacian operator, and then what are the frequencies corresponds to the Laplacian operator, or rather the eigenvalues of the Laplacian operator. So eigenvalues define the spectrum. And the peculiarity of the fractal structure is that these two dimensions do not have to be equal. In the regular hypercubic lattice kind of things, you can define both the position dimension and the momentum dimension. Momentum dimension will be the dimension of the Brillouin zone, for example, and they are always equal. But fractals are unusual in that case, that these two dimensions are not necessarily equal, and then you can have unusual possibilities. So, well, these are unequal, and on top of that, fractals are that this d, whatever it is not integer. That is why they are called fractals. So then the question comes that what is the value I should stick in this particular lower bound scenario, and that the lower bounds are always achievable in practice, but the scaling will be very different because these two numbers are not the same. And the answer is that the dimension which turns out to be relevant is the spectral dimension, because we are implementing essentially the Laplacian operator in the random walk, and everything is governed by the dynamics of that operator. What the physical space volume is, that is not the correct description as far as you want to calculate this quantity Q. Depends on the spectral dimension. Okay. So this is something which first argued analytically and then demonstrated explicitly by numerical simulations. And it's worth keeping it in mind that yes, there are all kinds of possibilities depending on the structure that you embed in this distributed database search. Okay. Yeah, so there is now one more mathematical feature which is useful for understanding applications. That yes, you can define this kind of spatial search, but can you really find its analog in physical systems? Mathematics is on one side, and then you take this interpretation seriously, that this Hamiltonian is actually going to be present in some physical system. Can you find a scenario like that? And then this results will give you an understanding of what can be done in this particular physical process. So for that, again, I will give some generic results. So for that, let me again go back first to the Grover's algorithm, which is very simple and implemented in a structure where all the eigenvalues, everything is explicitly known. So what are the results that we used? One of them is this evolution in the whole Hilbert space was restricted to only a two-dimensional space. The other components were initialized to 0 and they always remained 0. And then you could draw a picture and going it around a circle in this subspace, etc., as the evolution which arises. But now let us look at what essentially it did in the Hamiltonian language. So that can be very easily identified in terms of the properties of these two fundamental operators. Both are the projection operator, which is fine. So this is the operator which is going to be used as kinetic energy. So it has one the consequence of being a projection operator. One eigenvalue is 1, all the orthogonal directions are 0. And it's also true for the other object, which is also a projection operator. So what is happening there? This two-dimensional non-trivial stuff is going on, and there will be n minus 2 eigenvalues vanish. They are the orthogonal to this thing. One picked by this, other picked by that, and all the other stuff is 0. And then you have a nice evolution, and you can draw pictures about what is happening. But now look at in this breakup of kinetic energy and potential energy. Okay. So kinetic energy, lots of eigenvalues are all 0, n minus 1 are equal to 0, and one eigenvalue is positive. Same thing for the potential energy, n minus 1 eigenvalues are all 0, and at the target site, one eigenvalue is positive. Now, the algorithm is such that it works with this t equal to pi, which has a special condition that e raised to I pi and e raised to minus I pi, both of them are the same thing. They are both minus 1. So whether you call it positive or negative doesn't make any difference. As long as you put this evaluation, that distinction doesn't matter. But this is a kind of scenario that, yes, there are lots of 0 eigenvalues, one eigenvalue is plus 1, and when you introduce the potential, one more eigenvalue will change, but n minus 2 will just remain 0. Okay. So now you ask, these are the individual structures. So the eigenvalues of this operator which Grover defined, product of two operators. What are the eigenvalues? Well, just have to work it down as a two-dimensional matrix. We have written it in various different forms in the semester previous lectures, and if you work out the exercise explicitly, what you get, the pi is coming from the various convention, but these are the two eigenvalues or eigenphases rather of the Grover operator. So and this 2 theta is related to this rotation inside the circular trajectory. Every iteration you move by angle 2 theta. Because it's the eigenvalues are e raised to I 2 theta and e raised to minus I 2 theta in some manner. This pi is just going to put a sign in front, that doesn't matter, which is additional reflections and things like that are present. There is overall sign which changes various things. But main point is that there is a 2 theta and both the signs appear in front of plus or minus when you find out the eigenvalue for rotating in the two-dimensional plane. So this is the rotation and I convert it to an eigenphase because I wanted to interpret as the Hamiltonian. Eigenvalues were of this U operator. What can I say about the effective result in the Hamiltonian language? And there you see that there is a one value which will be positive and another value will be negative. So the interpretation is that it creates whatever sign convention you choose, a bound state in the spectrum. Remember, these were all kinetic energy. Lots of stuff was 0, but there were two other eigenvalues which are equal to 1. Now you find out that there will be one eigenvalue will be positive and one eigenvalue will go negative. Negative means below all this zero stuff. So zero energy is a free particle. There is nothing happening in the dynamics. We put a negative energy state, it corresponds to a bound state. And what the algorithm essentially does is this attractive potential at the target state creates a negative energy state in the spectrum. And you can work out, so these eigenvectors, you can find out whatever it is. I have a general expression which is something you can e raised to plus or minus I theta t minus s. A linear combination in the two-dimensional space, whatever it is, but these are the two situations that what you essentially did was created a bound state in the spectrum, and that helped in solving the particular problem. So this is an important lesson from the physical point of view, that this algorithm somehow introduces a perturbation. What is the perturbation? The attractive potential at the target state. And the consequence of that perturbation is that you create a bound state in the neighborhood or at that location or wherever the perturbation is. And that interpretation now can suggest where this kind of algorithm can be applied. Okay. And this kind of structure is actually far more general in many physical systems. And this is actually a very simple illustration of that what can happen. This is statistical mechanics. It is a, well, behavior which is similar to this, and I'm not going to give any proof of it, but it is worth knowing this result. And the label is something called Anderson localization. Anderson actually got the Nobel Prize for describing this phenomena in a very general scenario, independent of writing down explicit Hamiltonians or any of those kind of details. But what does that phenomena describe? And that is important. So what it does is, well, there are two words. Scenarios. One of them is called a strong localization, and it means that if you have a material with some number of defects, the propagating particles get trapped over there. And this can be strong enough so that something which is a metal can turn into an insulator. So and then there is a weak version where you don't have a drastic conversion of a metal to an insulator, but the amplitude of propagation gets enhanced at the site of defects, and that results slowing down of the propagation, or equivalent to increase of the resistance of whatever material in which the propagation is taking place. And what you are seeing here is something very similar. You are trying to make the wave function propagate through this space where there are certain targets. The targets can be interpreted as some kind of defects, and then the amplitude is going to go higher at the location of the targets, and it will not move much farther. Of course, these are all derived in the limit of real materials where the number of degrees of freedom are all infinite, and the densities of the targets is also infinite, and so on and so forth. What we have is only a two-dimensional subsystem where everything is happening. What is happening is quite similar. And this is a feature which is useful to know when you try to make a physical connection. These are the kind of features which can arise when you are trying to do this kind of evolution. And so now one can ask how I interpret in this scenario. All I am doing is basically just two different operators. One corresponds to the propagation or the movement by diffusion. The other can be labeled as something happening at the location of the defect. And that turns out to be quite good, and people actually then just went ahead and implemented this thing on a distributed lattice and tried to interpret the result in a language which looks like that. So what they observed for this kind of operator that this diffusion is actually quite general, but what you find is evolution is no longer two-dimensional You can play all kind of tricks, but the evolution is not going to remain restricted to this two-dimensional space. Some part will leak out. So this operator is different. It is not a reflection operator. But what you will still want to do is want sufficiently large component in two-dimensional to get useful success rate. If the too much amplitude is going to go out of the space, then the T is not in that external space, and whatever goes out of the space completely lost. You want everything to come back because T belongs to the two-dimensional space. So the leakage, it's unavoidable, but you don't want to get it much larger, or somehow you want to keep the leakage bounded. And for that, you need to tune parameters. Okay, numerically, if you want to do that, you have parameters in this diffusion process. You tune them so that the leakage is kind of kept under control. And the other feature is the process is where amplitudes are going to go up and down, oscillating. So analog of the whatever happened in the Grover's algorithm, you going around, round and round in circle. Okay. If you don't stop at the right point, you will not be reaching the target state. You have to figure out when to stop. So combine this thing, you have basically a numerical result where, so this is a success probability and this is time. You end up, right, well, this is actually, it hits a zero value quite well. So going into zero is not a big deal. But the success rate goes up and down and it decays. If you wait too long, that is because this amplitude is going out of the two-dimensional subspace. And so you have to literally tune parameters and also catch the stopping time where one of those peaks occur and find out what is the probability of success. It's going to remain a probabilistic algorithm. So parameters and it works. So many of the results which I kind of mentioned here, where I said that quadratic speedup is achievable with some proportionality factors over here, and these proportionality factors will depend on tuning those particular parameters to their best values, and that can be done in various ways. So, for example, one of the step is how many walk steps you want to take before the oracle. The DS is quite general. Walk step typically defined as a nearest neighbor connection, but I can say I want to take 2 walk steps before I use the oracle. I have a freedom to do that, and all those kind of things can be played around with to get the best result in terms of enhancing the probability at the target state, and you can derive bounds on it and get various scaling relation, etc. But this is the kind of a structure which emerges when you actually try to play around with the algorithm in a particular manner. And as I said, that people went quite further than that. So together with this implementation and this physical conversion, so the interpretation in terms of scattering at defects is possible. Where does scattering come from? Scattering comes from this oracle stuff, which you can again generalize. It is giving you some phase in the Hamiltonian interpretation, and you have alternative steps of diffusion and scattering. In the scattering process, you change the phases. So this is a elastic scattering, which is used in a lot of quantum mechanical phenomena, where the amplitude is changed only in the phase. The probability remains unchanged. That is, nothing is gained or lost. All you are doing is, it's a complex wave function, you can change the phase. And that phase is basically just coming from these angles, eigen phase connected to the corresponding Hamiltonian, like this, where some interaction is present. And since we are interpreting the target as a defect, the scattering is occurring at wherever the target objects are. And that leads to this kind of behavior that the amplitude at the location of the defects goes up and down. So okay. So now I can conclude in terms of giving some intuitive connections where we have seen this kind of behavior without worrying too much about how it occurs. So one of the simplest thing to connect this to is, suppose you have some material with a crack, maybe just a toy. And if you shake it at the right frequency, you know that the crack opens up. How does that happen? So somehow that energy of shaking has ended up in breaking the bonds which open the crack. Of course, you have to tune the frequencies. If you don't shake it at the right frequency, it will not open. But there is something you can do with some plastic toys or etc. You just shake it, it opens. And the phenomena is very similar to what I described over here. There is an energy which is there in the wave, which is that oscillatory shaking which you are doing. That energy is getting focused at the location where there is a defect. The crack is exactly the place where the wave propagation will stop. And at that location, amplitude enhances. It's a complicated nonlinear process afterwards, but it breaks up the bonds. Because mechanically, the larger amplitude corresponds to energy. And there are things which are holding together the material. Put too much energy, some bonds will break and the crack will open up. So this structure now can be said that we can use it to find defects in a material. It can be all kind of material. All you need is a vibrational test. And it can locate, so these are some connections. Of course, it will be dependent on the type of material property, and you have to design corresponding frequencies to do that, but it can be something which we can imagine that it is possible. There is another situation where this kind of behavior plays an important role, and it is still not fully understood in terms of details, but that is a phenomena of catalysis. And that occurs in various molecular reactions. What is the purpose of the catalysis? That you have a reaction which has very slow rate, and you add an auxiliary system to it, somehow the rate of reaction goes up. That auxiliary system doesn't change, it remains idle, but its presence is necessary. And you can make up models of this kind of energy transfer, which is enhanced because of the presence. We are not doing extra energy supplying or taking some energy out. We are just redistributing the energy available in various modes so that it goes into a particular reaction. And there is a very well-known phenomena which was observed in the 1960s by people studying chemical reactions. And it can be described in very simple fashion, that you have some chemical reactions where the molecules are connected by various kind of bonds between atoms, and the rate of reaction is changed by vibrational modes. How do the vibrational modes are implicated? It's a well-known structure or technique in chemistry that you can have different isotopes of the same material. And the isotope have same chemical structure. So the bonds of various connections between atoms are same. There is no change in the electronic part of the energy. But the isotopes changes the masses of the nuclei. And so if the vibrational modes are involved, the values of the frequencies of the vibrational modes depend on the mass, nuclear mass, not just the electronic structure. And what was observed, this goes under the name of Heimer effect, or actually there is another name for it. I think it is called kinetic isotope effect or something like that. Yeah. That people actually measured the chemical reaction rates as a function of the isotope masses, and they found a dependence. So reaction rates depend on the isotopes. And there is no way to explain them other than saying that the vibrational modes are playing a role. Otherwise, nothing depends on the masses of the isotope as far as the electrons are concerned. And so how these vibrational modes are changing the rates of reaction, it's an open question. One can make up models like this where there is some energy from the vibrational modes is getting focused, and what is doing that job is this catalysis, and what the job of the catalyst will be is something like what I described in explaining Grover's algorithm in the previous semester, just a reflection operator. You can do it with bouncing masses and all those kind of things. So it doesn't absorb anything, it just reverses the motion just at the right moment. That's what the parameters have to be tuned. But if you are able to do that, then the amplitude will build up, and then in the catalysis, the amplitude will go into the energy function, because the energy is just amplitude square in this mechanical interpretation. And once you have enough energy, the reaction rate will get affected. And it can be dramatic because the amplitude or the energy is now going to go into the exponent as far as the catalysis description is concerned. And lots of measurements have been made, and the largest effect is seen in case of hydrogen. For the very simple reason that going from a hydrogen to a deuterium, mass changes by a factor of 2. That's the biggest change you can have, just the next isotope. The other isotope, the ratio will change, but by a smaller amount. But the large effects have been observed in a lot of these bonds which involve hydrogen, and well, how well we can understand it, it's an open problem. And you can ask the inverse question also, that if I understand the dynamics in detail, can I design new kind of catalyst? Very heavy and important problem as far as all kind of chemical industry is concerned. So that is another connection of this, well, all over the place, spatial search and amplitude amplification process. They can have all kind of connections, and yeah, I didn't want to give too many mathematical details, but this physical ideas are all important, and it has probably unexplored applications which can be very interesting. So yeah, I will stop here today.